If you have written Go for more than a week, you have heard the pitch. Go routines are cheap. Spawn thousands of them. The scheduler handles it. That advice falls apart when the work is CPU-bound. Tasks like image processing or cryptographic hashing. On a 4-core machine, using 500 workers for a CPU-heavy task can drop your throughput by 40% compared to running just 4. This chart shows the performance limit in real time. Throughput climbs efficiently until we hit 4 workers, then it begins to plummet. Every worker added past this point makes the system slower. This is the Go routine scheduler cliff. Over the next 5 minutes, we will refactor a sluggish worker pool into a hardware-aware system, build a concurrency semaphore, and verify the gains using Go's internal telemetry. We are moving past the idea that memory is the only limit on concurrency. For CPU-bound work, the physical boundaries of your processor dictate the speed of your code. We'll start with a baseline experiment, processing 100,000 SHA-256 hashes through a standard worker pool set to 500 workers. The terminal shows the result, about 1,100 jobs per second. Even though the machine has plenty of free memory, the hardware is clearly underperforming. To understand why, we look at the Go runtime. This is the GMP model. 4 squares represent physical CPU cores. The scheduler funnels 500 workers into 4 slots. Since only 4 execute at once, 496 wait. To be fair, it cycles them thousands of times per second, pausing, saving state, and loading the next. This creates a massive penalty called cache thrashing. Every time a worker is swapped out, its data is flushed from the fast L1 cache. When it returns, it has to fetch that data from slow main memory, wasting thousands of CPU cycles. At 500 workers, the Go scheduler is working harder to manage the queue than it is to actually process your jobs. The solution is to remove the hard-coded worker limit and align our code with the machine's actual capacity. Instead of an arbitrary number, we use runtime.go_maxprox. This function allows the program to fetch the exact number of logical processors available. By passing 0 to the function, we retrieve the current setting without modifying it. Hard-coding worker counts is a liability in cloud environments. If a Kubernetes pod is moved from a 2-core node to an 8-core node, a static number like 4 will leave half the CPU idle. Tethering the worker count to the hardware ensures the pool scales automatically. Whether the service is on a laptop or a high-end server, the concurrency remains locked to the machine's actual limits. You may encounter scenarios where you don't control worker creation, like an HTTP handler that spawns a new Go routine for every incoming request. In these cases, we use a semaphore. This is a buffered channel that acts as a throttle for the CPU-intensive parts of the code. We define a channel with a buffer size matching Go maxprox. Before the heavy work begins, the Go routine must push an item into the channel. When the work is done, it pops the item back out. This doesn't stop the system from creating thousands of Go routines for incoming traffic. Instead, it ensures only the optimal number are actively using the CPU at any given millisecond. The semaphore acts as a choke valve. It forces access requests to wait in a parked state, preventing them from degrading the processing speed of the entire system. Optimization requires measurement. We need to verify exactly how the runtime behaves under load to confirm our changes are working. Go provides a telemetry tool called sketchtrace for this purpose. We activate it by running our app with the environment variable godebug=sketchtrace. This allows us to compare the original 500 worker run against our new, right-sized version. In the top log, the run queue metric is 347. This is proof of massive scheduler overflow. Hundreds of Go routines are stuck in a global queue. In our new version below, run queue is 0. The work is flowing without a bottleneck. We also see that idle prox is 0. This confirms that every available core is fully engaged in doing work, rather than waiting for the scheduler to catch up. Sketchtrace provides the definitive evidence that our concurrency model is now perfectly aligned with the hardware. By limiting our pool to 1 worker per core, the final benchmark shows 1,950 jobs per second. That is an 80% throughput increase, achieved by removing 496 workers. Go routines are virtually free to create, but they require expensive physical CPU cycles to schedule. Remember that this 1-to-1 rule is for pure CPU-bound tasks. If your Go routines are waiting on database calls or network requests, you can safely use hundreds of workers. In those cases, the Go routines spend their time parked, not competing for the CPU. Writing high-performance Go is a matter of respecting the physical limits of your hardware. When you work with the machine, the speed follows.